Hello. The title of the slide, the subject is Design and Analysis of Reconfigurable Systems. So the group members are Anil Shankar and Sujantani Manohar. The project overview. FPGA are widely used to accelerate compute-intensive and parallel algorithms. Cryptographic algorithms such as AES particularly benefits from hardware acceleration. The project demonstrates a complete hardware-software co-design on SoC FPGA. So we are implementing AES-128 encryption on DE1 SoC board. So this is encrypted and then decrypted using the HPS software. So we are integrating HPS on the DE1 SoC board using memory mapped AXI interface. And then we validate the hardware output using software golden reference. So over here, we are going to look at the hardware software system architecture. Um, this is implemented on the D1 SoC board. So as you can see here, it is having MP RAM based subsystems, and then which is having a shift row, mixed column, add round key. So with this architecture, we'll just pass an encrypting key, and then we will take out a decrypting key. So the block diagram here is that we are giving a user input. This is done through the terminal, and then the HPS software reads it. After reading it, a random key is being generated. And then we do have a plain text input, which is further processed into software AES golden reference, which can be further decrypted. So the HPS software processes this into, as in it emulates this into FPGA board, that is DE1 SoC board through AXI Lite, which can do AES 128 encryption, which is further ciphered text return to HPS. So the HPS responsibilities are as follows, which is of generating 128-bit AES key at runtime, reading up to 16 ASCII characters, and then pack and plain text key into 32-bit registers, send data to FPGA, receive ciphertext from FPGA. So this is the AES software implementation. So software AES based provides free reference implementation. It supports 128 with 4 keyword and 10 rounds. It implements all 4 main AES operations and subsystem shift rows. Use the key expansion module to generate round key. Encryption runs over multiple clock cycle. An important design choice we made was to have FPGA handle encryption only, while decryption is left to HPS. So AES implementation using Verilog RTL. So this is the flow. So plain text of 128-bit is taken in, and then you're having the key expansion, which is like divided into K0, K1, K2 to Kn, which is processed through different rounds to cipher the text. So AXI4 light memory mapping. So from address 0 to 3, we map plain text to 128-bit. Address 4 to 7, we map ASCII 128-bit. Address 8, we start encrypting. Address 30 to 35, ciphertext 128-bit. Address 36 denotes the done flag. So the workflow is described in this slide. So this is the operation flow where HPS writes key and plain text, and then this toggles to the start register, and then FPGA encrypts the data. Then FPGA like raises the finish flag, and then HPS reads the ciphertext. So hardware software co-design. User enters plain text. HPS generates random key. HPS performs software encryption. HPS sends data to FPGA. FPGA performs AES encryption. FPGA returns ciphertext, and so on. So these are the implementation result. As you can see here on the left, you can see the terminal output showing generated key and plain text and both software and hardware ciphertext values. On the right, we see decryption verification. Notice that the hardware ciphertext matches the software ciphertext, confirming the correct encryption. The decrypted text matches the original output. So the FPGA results shows the successful synthesis of the implementation. The first one shows the compilation with no errors. So and then the middle section shows that resource utilization with a reasonable amount of ALM and registers. So the conclusion is that successfully implemented AES 128 hardware software co-design, correct end-to-end encryption and validation. Challenges faced are NDNS mismatch between HPS and FPGA, AXI register alignment, and offset. So the future work here is add AES decryption in the hardware, support other precisions or modes, pipeline optimization for higher throughput. Thank you.